So I want to talk about basic bucket sort. So we'll go through kind of a messy example of some work I used to do, and it's an example of a non-comparison based sorting. I used to work at a store that sold t-shirts. Although we sold several different sizes of t-shirts for this example, I'm just going to focus on 3 different sizes. We sold large t-shirts, medium t-shirts, and small t-shirts. And all of our t-shirts had logos on one side and they were blank on the back. So part of keeping our store neat and tidy and organized was we would have to make sure that t-shirts were sorted. And the easiest way for people to shop for a t-shirt is to shop for their size, and then once they find their size, maybe find a color or a logo or a pattern that they're interested in. So most stores organize clothing by size. So one of our challenges was at the end of the day, people would have been shopping. They would have pulled the shirts off of the racks and off of the shelves, and they bring them up to the counter or put them to the side. And at the end of the day, we have a whole jumble of t-shirts of varying sizes, and we have to reorganize them and put them back on the shelves in their appropriate category by size so people can find the size they're looking for, and then once they find their size, look for the appropriate pattern. So we had a pretty straightforward approach for doing this, and our approach would be considered a type of bucket sort. So we would go and we'd get a couple of big cardboard boxes, one for each size of shirt. So we'd have a box for the large shirts, the box for the medium shirts, and a box for the small shirts. And then we'd gather up all of the shirts from the shop, and we'd put them in a pile. And we'd just go through the pile, basically from top to bottom. So since we're talking about algorithms, let's think about the complexity of this. So the complexity of this actually was kind of our real life time spent reorganizing our shop. So we would go through and we would pull a shirt off of the top of the pile. We'd find a logo on it and we'd put it face down in the appropriate box. So we'd repeat this. Notice that I'm not doing any comparisons, and the boxes are all real close together, so it takes almost no effort to grab a shirt and put it in the appropriate box. So you might already be thinking about how much effort I'm doing here. So basically, if I've got n shirts, I'm touching each shirt once. So that kind of represents the amount of time I'm spending. Okay, and then when we're all done, we would have to go through our different piles, and we'd either have to fold them or put them on hangers. So we would maybe take all of our large size shirts, and we'd go through them and tidy up that pile one more time. We wouldn't necessarily organize this pile any further. We'd oftentimes just leave them unordered based on their colors kind of scattered around, because it was pretty easy for people to look at the shirts and look at kind of the easily pick out the color that they were interested in. Okay, so I've now organized all of my large shirts. I can go through, do the same thing with my medium shirts, kind of go through the pile one more time. And notice again, I'm still basically touching each shirt just one more time. So it looks like by the time I'm all done, I will basically touch each shirt exactly twice. The effort to put them in an individual box was pretty minuscule. If we were doing this in a computer, using an array would give us that random access property where we can easily put something in an array, or if it were an array of linked list, we could easily append things onto the appropriate linked list. Okay, so this variation of bucket sort, where we were just trying to categorize things based on a single property on their size, basically is an order and search. We had to go through and put each shirt in its bucket, which if we can easily append to some sort of a container, is order one time. And then we had to go through and take everything out of the buckets and tidy them up into a nice neat pile. And again, we basically went through each item once. If it's easy to remove them, by the way, the buckets were acting like a queue, a first in, first out sort of data structure. If it's easy to remove them, then we can easily put them together and have our data completely organized. Okay, there's an interesting property of this bucket sort that I want to talk about. It's one of our sort properties that we haven't yet covered. So again, I've got a little set of shirts here that I need to sort out, and I'm going to go through them just like I did before. Remember that the buckets basically represent queues. They're first in, first out, and that's important to the property that we're discussing now. So I'm going to go through each one of these. So I've got a purple shirt, so purple small, orange medium, kind of aqua small, and a green small. Okay, one of the things I want to point out here is that when I take things out of the small bucket, they are in the exact same order that they were in my original pile. So if you remember, my original pile we encountered the purple small first, followed by the aqua small, followed by the green small. Okay, so that idea of is the concept of being a stable sort. So we had 3 different items that we would consider to be identical for our purposes of sorting. They were all smalls, so we would consider them basically equivalent. They all belonged in the small bucket. But there were other things associated with them, other important facets like their specific color and the specific logo. And when we were all done sorting, this particular variant of sort ensures that they maintain their original order from our original pile with respect to those secondary characteristics. So that basically is referred to as being stable. So this form of bucket sort that we've been looking at is a stable sort. It turns out there are some types of sorts that just cannot be made to be stable. So we've already encountered one of those. Heap sorts can't be guaranteed to be stable. But there are lots of other types of sorts that if they're implemented carefully can be stable. So we classify a sort as either stable or not being stable based on whether it can be implemented in a way that ensures this idea of stability, of keeping items that are considered to be identical in their original order. Okay, so again, stable sorting is a sorting algorithm that maintains the relative order of records of equal keys. So in our t-shirt example, the key, the thing that we were sorting by, would basically be the size of the shirt, and then those secondary characteristics like color or pattern would maintain their original order from the pile that I pulled them out of. Okay, so Wikipedia has a list of several different sorts that are considered to be stable. This isn't an exhaustive list, but it does list the idea of a bucket sort. By the way, keep in mind that our bucket sort was stable because we were doing a first in, first out queue for the buckets. There would be ways to implement this differently that would break this stability property. Okay, so let's be just a little bit more formal talking about bucket sort. So the sort that we've just used in an example is actually only kind of partially bucket sort. It's missing a potentially important step. So one variation of bucket sort does a little bit more work than we just did. It does set up the initial buckets or boxes in my example, and again, those were kind of a first in, first out sort of data structure or queue. It then goes through the scatter process where it goes through everything in our input data and puts it in the individual bucket. Or my example, that was putting it in the box. Then once it does that, it goes through and sorts the contents of each individual bucket. So that was something I didn't do. I didn't go through and once I had all the small shirts organized, sort them by color or logo or whatever other secondary characteristic I want to sort them by. Then in this more comprehensive form of bucket sort, it still does what we did at the end. It kind of gathers together the contents of all of the individual buckets. So this variation of bucket sort is a little bit more powerful than the example we did. It gives a more complete ordering of items, but it does it by relying on an intermediary sort of the individual buckets, and that will have an impact on the overall time complexity. So it's kind of an interesting example to look through some of the variants here and think about the various parameters that impact the overall time complexity. So we see a little bit more complicated variation of performance here than we've seen in some prior cases. So we have to consider the number of different buckets that we have available, and that will impact performance. If instead of just having 3 sizes of t-shirts, we had 1,000 sizes of t-shirts and only 5 different t-shirts to sort, then our number of buckets would be 1 per size, 1,000 different buckets, and the effort it takes to put our handful of t-shirts into those buckets would overwhelm the benefits we just saw with our simplified bucket sort. Okay, so when you're considering things like bucket sorts, you really have to think carefully about the number of buckets that you may have versus the number of data elements you have and the interaction between the two. And you also have to consider whether you want things in a more comprehensive order, which may require a little bit more work than the example we just did.